Test.
Well, we need somebody.
You'll have to have somebody. Yeah, no, sorry. What I mean is
Yeah,
eventually turn the
30 seconds later, too.
I'm muted at the moment, so.
Okay.
Feedback.
Try it again.
Test. It might take 30 seconds to pair. Yeah.
Yep, I hear you.
All right.
Wonderful.
Perfect.
And hopefully this won't be too distracting to you.
Well,
Yeah, okay. And then doesn't have to be here, it can be like here. You don't need to see this, it's like to go.
let me minimize that.
Mhm.
And then this.
Okay. Good luck. I guess if you're in a crisis, give me a call. I can rush back down.
Okay, yeah. Sure, I don't see any.
Good luck with some of this.
All right, great.
My 9-year-old daughter called me to ask me to come home. I was gone last week. I'm gone again next week. So she said, "Daddy, I can see you come home."
Mm. Okay, I've unmuted.
Welcome. Good morning, sorry. Good evening, everyone. Sorry, we'll cut that part out of YouTube. Let me restart. Welcome. Good evening, everyone. My name is Heidi Wu. I'm your host tonight. I am an astronomer and an assistant professor in the physics department. And today I'm very excited to be introducing Dr. Andres Salcedo from University of Arizona. So Dr. Salcedo receives his bachelor's degree from Lehigh University and PhD degree from The Ohio State University. And he has won many awards in both Lehigh and Ohio State. Most notably, Dr. Salcedo received the prestigious Computational Science Graduate Fellowship of the Department of Energy. So Dr. Salcedo's research is in cosmology, the study of the universe, which you will hear a lot about. During his PhD and postdoc years, he has made important contributions in several fields in cosmology, including galaxy clusters, galaxy formation, and large-scale structure in the universe. In particular, he has developed unique tools to help analyze the data from big telescopes. Dr. Salcedo has a very impressive list of publications and has spoken at conferences and workshops around the country and the world. Please join me in welcoming Dr. Andres Salcedo.
Thank you for the introduction. That was very nice. Hello. So yes, I will be talking about cosmology, and I'll be specifically talking about cluster cosmology. So I will just go straight into it. Okay, that should have changed there. All right. Yeah, so cosmology, the study of the origin and development of the universe. So I've listed some key cosmological questions on the right. Many of them we have answers to, and then others, I mean, let's just say that there are incomplete answers to all of these. So how old is the universe? What is the geometry of the universe? Is it expanding, contracting, or static? What are its contents, and how are these contents structured? So today we actually do have, like I said, a partial answer to these questions. And that answer is basically this model called lambda CDM. So it's sort of a standard model of cosmology. So the features of the model are that the universe is geometrically flat, that general relativity governs the structure formation. It's expanding, so that answers the question in the lobby. And it contains contents of matter and energy. So nowadays, the matter energy budget of the universe is basically made up of 5% baryonic matter. That's the kind of matter that we are. It also is the matter that stars and galaxies are made out of. 25% dark matter, that is the CDM in lambda CDM. So CDM stands for cold dark matter. That is the vast majority of the matter in the universe and can only be studied through its indirect, basically inferred through its gravitational effects. And then the vast majority of the energy budget is dark energy, which is basically this lambda. And it's believed to govern the accelerated expansion of the universe, but it's very unknown. And so I've also put some plots here, and this just shows the sort of the energy matter budget of the universe at different times. So here, what I've just talked about is this pie chart on the top. And the only thing I wanted to illustrate is that you can see that here for this pie chart from 13.7 billion years ago, the contents of the universe were very different. So we were dominated by dark matter, and even neutrinos made up a significant contribution to the matter energy budget. So basically my goal of this talk is to try to convince you of those bullet points that I just showed. So let's start with general relativity or gravity on cosmological scales. So the prehistory of this theory goes back to the 19th century of mathematicians who basically started developing theories of geometry that questioned some of Euclid's postulates, specifically the ones dealing with parallel lines. So here, so sort of people that were involved in this are like Gauss, Lobachevsky, Bolyai, Riemann. But here I've sort of shown kind of a picture of these kind of three ways of doing geometry, right? So the middle is called Euclidean geometry. This is the geometry of zero curvature. And then you have hyperbolic or elliptic geometries. Oh, sorry, I should be motioning with the pointer. My mistake. Elliptic or hyperbolic geometries that basically are the geometry on curved surfaces. So you can see that you have these different little descriptions, right? So the sum of angles in a triangle differs in the different geometries. The circumference of a unit circle differs, and parallel lines behave differently. So this is kind of, so, you know, we all learn about this Euclidean geometry in school, right? So these are sort of outlandish seeming, but it turns out that about 100 years in advance of these people working on this, it became very important to physics. So its importance was because the sort of theory of gravity that we believe governs the universe is a theory of gravity that's based off of these non-Euclidean geometries. And so that's called general relativity, developed by this famous guy, Einstein. And I've shown just one equation. So this is called the field equations. And what the field equations do is they basically relate the geometry of the universe on the left to its contents. And you may notice that there's also this lambda here. So this is this infamous cosmological constant that has to do with the accelerated expansion of the universe. So these field equations were proposed in 1915. And then it took a few years for a guy to come up with the solutions that we use today. So this guy was Alexander Friedmann. He was a Russian meteorologist, in fact, mathematician, meteorologist, airplane factory manager. He had an interesting life. So he basically developed solutions to these equations that we are sort of still using today. And so here I've just written one of these Friedmann equations, as they're called. And here what we're relating is basically the expansion of the universe, its contents, and its curvature, right? And so the last important fact that I want to talk about from general relativity is that it predicts something called gravitational lensing. So what this is that it's basically the fact that matter can bend the path of light. So here I have a diagram of sort of a source and a lens, right? So here we are on Earth. Here is a galaxy very far away, a source galaxy. And in the center, we can imagine that this is a cluster. So this is the lens in this gravitational lensing. And you can see that light rays that are traveling from the galaxy can be bent by the lens, by the matter in the lens. And so now we can look at an actual cluster on the right. So this is Abell 1689. Abell is just refers to a catalog of many clusters. And you can see that there's sort of the center of the cluster around here where I'm motioning to. And then if you look around, you can see that there's these sort of weird distorted images tangential to the tangential to the distance towards the cluster, right? So for instance, here, this is basically a galaxy that has been gravitationally lensed and done so strongly that its image has been basically sheared out into this ring. So that's an example of what's called strong lensing. And what we utilize very frequently in cosmology is something called weak lensing, which is far more subtle distortions of galaxy source images tangential to the radius of the cluster. And basically what this allows us to do is map out the matter within clusters, and on large scales map out the matter distribution of the universe. Okay, so now I will talk about sort of parallel developments in cosmology. How do we learn how the universe is expanding, right? So one of the things I said is that part of the lambda CDM model is this notion that the universe is expanding. So this has to go back to turn of the century, and this astronomer Henrietta Leavitt basically discovering rung on the distance ladder. So you maybe have heard of this distance ladder. So sort of the very bottom of it is parallax. It's a geometrical way to measure distances. So you can actually demonstrate it yourself. If you put your thumb in front of your face and close one eye and then the other, you can see that the image moves, right? So that's right in front of your face. Now you can focus on some more distant feature in the room and do the same thing. You'll see that the apparent movement is much smaller. So that's basically this is sort of a geometric way to measure distances to astronomical objects. you can imagine that in this example, your nose is the sun and your eyes are the earth traveling around the sun, right? So the distance ladder then is sort of trying to bootstrap from one of these ways to measure distances out to others. And so a very early rung on the distance ladder is what are called Cepheids. So here, I'm actually showing you the plot that she used to establish this correlation between the magnitude of these Cepheids, which are sort of a class of stars, and their pulsation period, right? And so since the pulsation period is something you can measure regardless of distance, you can then back out the distance from the magnitude. And this is a very nice straight line. So this is important to cosmology because this rung on the distance ladder allows us to get another one that get up to the next rung that allows us to measure cosmological distances. So, right. And these Cepheids also are important at the turn of the century in sort of establishing certain facts about our place in the universe. So in the 1920s, there actually was this great debate actually refers to a literal debate in a room between these two guys. They each had 40 minutes. So Harlow, Shapley on the left, Heber, Dowse, Curtis on the right. And basically what they were, at least one of the things they were arguing about was whether or not the Milky Way was the extent of the universe, or whether or not there was stuff external to the Milky Way. And so one of the points of this debate was whether or not Andromeda or M31 was inside of the universe, or sorry, inside of the Milky Way or external to it. And so just a few years later, this fellow here, Hubble, basically settled the debate by using Cepheids in Andromeda, which I've shown here. So basically he was able to measure the distance to Andromeda using Cepheids within Andromeda and establish that Andromeda was definitely outside of the Milky Way, and therefore that the Milky Way is not the end all be all of the universe. So shortly after that, Hubble and others, so Humason and Slipher, also used Cepheids to establish the expansion of the universe. And this plot here is actually from this paper that Hubble published. And this is showing basically velocities on the y-axis and distances on the x-axis. And you can see that there's a clear relationship, right? So things that are further away from us, for instance, up here, are moving away faster. And this is expressed with this equation. So you have velocity, and it's in proportion to the distance, and the factor of proportionality is what's called Hubble's constant. So this is basically how the expansion of the universe was established as an observational fact, and it depended critically on the calibration of these Cepheids. Okay, so now sort of the third question that I want to answer is, how did we learn the universe is full of dark matter? So I actually show these three guys because this is sort of an early example of a dark matter hypothesis, right? So in cosmology, when we talk about dark matter, we're referring to cold dark matter. It's believed to be non-baryonic. But I think that the example of Neptune gives you an idea, should sort of serve as an analogy to how we've figured out that the universe is full of dark matter. So in the 1840s, this man, Urbain Le Verrier, and actually also John Couch Adams, around the same time, realized that the motion of Uranus had discrepancies in it. And so they hypothesized that there was some dark companion to it, right? Which turned out to be Neptune. And so what happened is that the English astronomer, Adams, contacted one of his friends, and his friend failed to find Neptune. And then shortly thereafter, the French astronomer contacted a German astronomer, Johann Gall, and he found Neptune basically immediately within a degree of where Urbain Le Verrier's calculations predicted it to be. And then there was an argument about priority, but now it's sort of accepted that both of these guys have equal claim to the discovery. But the reason that I put this up here is because this is basically the idea. This is essentially the way that we've inferred the presence of non-baryonic dark matter. So we look at the dynamics of galaxies, and we find that there is a discrepancy with the amount of light we can see. And so we infer the presence of some other matter. So in the case of sort of cosmological dark matter, this story begins in the 30s with this fellow here, Fritz Zwicky. And so what he did is he looked at the Coma cluster, which I've put an image of here. And he actually only had, I believe, 8 spectra. But with those 8, he was able to establish that essentially the velocities of the galaxies were much too fast for the amount of mass that he could infer through light, right? So he assumed a mass to light ratio. And so then he basically sums up all the light, assumes that a certain amount of mass is required to make that light. He gets some kind of measurement of the cluster mass from visible light. And then he compares it to the velocities that he can also measure. And he finds that the velocities are way too big. So here I put just this equation. This comes from the virial theorem. And you can see that there is a relationship between the velocities of objects within a cluster and the total cluster mass. So his conclusion then is that there must be, as he called it, Dunkle materia, or dark matter in German. And this discovery was basically not considered a crisis for about 40 years, but this is sort of the first observational detection of dark matter, right? And I will point out that at the time, he did not think that it was not baryonic. To him, it could have been just brown dwarfs, perhaps. I mean, all he was saying is that there was a discrepancy between the mass inferred from light and the velocities that he could measure. So shortly after him, actually, people started doing simulations of galaxy dynamics and galaxy interactions. And this becomes important to the whole story of sort of the kind of cosmology I do. And also it's relevant to the discovery of dark matter as well. And I think it's very cool. So what I'm showing here is a plot from a paper that a Scandinavian astronomer, Eric Holmberg, did in 1941. And so what he did is he actually took light bulbs, right? And he put them down in some configuration. And then he used the light emitted from the light bulbs to calculate the gravitational force from between his particles, right? So light is a 1/r² law. Gravity is a 1/r² law. There's a whole sort of engineering problem to make sure that the setup, the paper is non-reflective and all this. But the idea is that you can basically very efficiently measure the forces between particles / light bulbs in this way. And you can do simulations of galaxies. So here he has one of his simulations where he has 2 galaxies that are rotating opposite to each other and are also passing. And you can see actually that as he sort of evolves the simulation of light bulbs, he gets something that looks sort of qualitatively like real galaxies. So you have actual spiral arms. And here on the right, he was not trying to reproduce this behavior directly, but you can actually find pairs of galaxies in the real universe that more or less look like his light bulb setups. So I think that's very cool. And I believe, though I'm not certain, because you have to, probably read every single paper to be certain, but I believe that this is the first M-body simulation ever run. So, yes.
There's no pictures of his physical light bulbs floating around somewhere?
Like photographs, I'm not sure. In the paper, there are sort of diagrams. Yeah, it is too bad. I would love to see them. Yeah, so, okay, so now in the 30s, Wiki found this discrepancy in the Coma cluster. Basically, it was not taken that seriously. Just because I think, so first of all, it was based on a very few objects. Mass to light ratios, I think, were probably uncertain at the time. And in any case, it was a single paper. So no crisis, there was no sense of a crisis, right? So now we fast forward to 1971, and also coming from this Holmberg paper, right? People are doing simulations of galaxies. And here is actually an example of one. And so here I'm just showing you sort of a representative spiral galaxy. It has a bar as well. And on the right-hand side, you can see basically snapshots of this simulation that was run in Princeton. And so here up in the top left is the beginning. So you just have a ball of these particles, and you're going to basically on a computer calculate all the forces between particles and update, right? And simulate the dynamics of a galaxy. And so what happens is that you can see if you go from left to right and then down, that you start to form something that looks like, the galaxy on the left. So for instance, in this panel, you have an obvious bar and you have spiral arms, but the issue is that they're not stable. So you form them, but they immediately dissipate. right? And this was perceived as a problem. And the solution to it actually was what's called a halo. So at this time, they didn't specifically invoke dark matter, but they said that given our simulations, we can't form stable arms and bars, but a solution to it, and this comes from different people at Princeton, Jerry Ostraker and Jim Peebles. The solution to this is that you can have what's called a halo potential, so it's a large scale spherical potential. And if you have the galaxy embedded within that gravitational potential, you can form stable bars and arms, right? And so this is not a direct detection of dark matter, but it's pointing in the direction to the solution to all these problems, the Coma cluster, the instability of the bars and arms. So the direct evidence came from Vera Rubin, who is here on the your right-hand side, and her collaborators. And what she did is she measured the rotation rates of galaxies. And so what she found is that here we see on the left-hand side, this is just sort of a example, right? But it's representative. So you have the velocity as a function of distance from the center of the galaxy. And so in the yellow, you have observations from starlight. And then in the blue, you have observations from the 21 centimeter line in hydrogen. So this was enabled by sort of the birth of radio astronomy in the middle of the 20th century. And so you can also see this dashed line here, which says expected from visible disk, right? So again, you're trying to infer the amount of matter from the light that it emits. And when you do that, you get sort of a mass distribution. And from that mass distribution through this virial theorem, you can predict what the velocity curve should look like. And so you see that it obviously falls off if you only account for the matter that comes from the matter that's emitting light, right? But what's observed is that it's flat. So this is sort of the most direct evidence for dark matter that I would say convinced sort of the larger community of astronomers that there was a need for this. And here we can just look at more rotation curves because I think they look very nice. And these are actually here. This plot here is the actual, I would say probably the most convincing plot historically, right? So her first paper, I think, did not have very many galaxies, but just a few years later, they published a paper with 21 curves, and in every single case, there's no drop off. And then here on the left, you can see that for an observed galaxy rotation curve, you have a component that comes from the disk, which is observed, and then you also have this halo component, right? And this halo component was found by the simulators to be necessary to have stable bars and arms. So now I'm going to start talking about sort of my research. So one of the key questions is, how do we study a mostly dark universe, right? So I've told you that only 5% of the 5% of the energy matter budget of the universe is luminous, and the vast majority of the matter energy is dark, and therefore has to be sort of inferred from its dynamical and gravitational effects. So I'll actually show you example simulation of the universe on large scales. So here, this is basically run by a computer. And what you have is tons of particles that each represent some amount of matter. And what the code is going to do is compute the forces between them and then update their positions and velocities over many iterations. And then eventually you'll have an output that is sort of a simulated distribution of matter at the present day. So here there's a scale, 125 megaparsecs. I've converted that into miles. So quintillion is 10 to the 18 miles, 20 quintillion miles. And here we can see, yes, I've written here, this is the Millennium simulation. And this snapshot is from very early in the simulation, 13.4 billion years ago. So what you're seeing is basically you have a more or less smooth distribution of matter. And there's some anisotropies. There's some, here's maybe the beginnings of a big peak. Here's sort of a region that has slightly less density. And now I'm going to flip through a few snapshots. So you can see that basically these early peaks are enhanced by gravity to form these structures. So here's another snapshot, even further. So now you have the beginnings of what are called halos. Here's an extremely big one here, and you can see that there's maybe small ones, halos that are falling into the potential of this massive neighbor. And then here is sort of the expected matter distribution at the present day. So this is referred to as the cosmic web, and it has a few features. So you can see again that there are these massive distributions of matter that are referred to as halos. So here's probably the biggest that we can see in this snapshot, but here's another large one, and they are sitting at the sort of the nodes in this web, right? So between them, there are what are called filaments, right? So you can see that there are these filamentary structures of matter connecting the huge halos. And then in between the filaments are what are called voids. So here, for instance, is a particularly big void that is basically empty of matter, right? So what has happened is that in the early universe, you had a mostly smooth distribution of matter with some little fluctuations up and down. And through the force of gravity, basically, you've enhanced the sort of little peaks in density. And then for the troughs, those have become basically evacuated of matter and have turned into voids. So here is, a zoom in on what would be a galaxy cluster. So this is just showing you the matter, but you can imagine that you would also have baryonic matter that's fallen into this potential and formed into galaxies, stars, and all the rest of it. So how we study this, I like to show this analogy, right? So you can imagine, if you were an alien, right, and you came to Earth and you knew nothing about humans at all, right? What would you see, right? You would see basically the light that we emit in our cities, towns, all the rest of it, right? And say you wanted to, keep your presence secret, all you would be able to do to study us is to study this distribution, right? But as it turns out, you actually can learn a lot, right? So I just showed the population density of humans that we know on the Earth today. And if we just flip to the light, you can see that they obviously trace each other, right? So humans emit light, right? But there's no constant relationship between humans and lights. It's not like we're all holding a single light bulb, right? But you can learn a lot from this map already, right? You can theorize, okay, so what can we learn, right? So there are obviously parts of the Earth where humans don't live. We don't live in Antarctica. We don't live in deserts, right? So you've already learned something about our biology. We don't live in the ocean, right? And we have cities as well. And actually, the cities also are formed from, human history. And for instance, you might notice that large cities tend to be on the coasts. They might be on rivers. Now, we know the reason for this because transporting stuff over water was more efficient, hundreds of years ago. So this is kind of the analogy to what we have to do in the cosmology case, right? So we can see the light, but what we're really interested is in the underlying distribution, right? So light traces dark matter. In this case, light traces humans. So here's an example of this. So here we have another simulation, and this is of the dark matter distribution. And so what basically the whole game here is coming up with models that make this mapping from dark matter to galaxies or to whatever tracer it may be, right? And so you can see that someone has taken the left-hand distribution and applied a model of what's called the galaxy halo connection. This is basically a fancy term for the relationship between the light and the dark matter. And you get what's shown on the right. So you have a distribution of galaxies, and this is still sort of a model, but this should sort of be consistent with what we actually see. And so basically a huge part of cosmology is developing these models and calibrating them and validating them. So here's an example from my own work. So on the left-hand side, you actually see a footprint of galaxies. And on the right-hand side, you see a model of the galaxy halo connection applied to a dark matter only simulation. And so you can see that the model works fairly well. So you have features in the data map of galaxies that reappear in the model. So basically designing these models is a huge part of what cosmologists are doing nowadays. So, right. So how do we use clusters to study cosmology? Just to extend the analogy a little further, clusters are basically like, the biggest cities on Earth, right? So clusters are huge distributions of galaxies, and they are embedded within the largest peaks in the dark matter distribution. So we can just appreciate a couple images of clusters here. So you can see that there's a central galaxy in the center of the cluster, and there are a bunch of members or satellites, and that the members tend to be red. So the way that we identify clusters is by looking for these large overdensities of red galaxies. So here's another one. They're just beautiful pictures. So there's a few more facts that I want to tell you to explain how we use clusters to study cosmology. One of them is this detection of the CMB. So in the 60s, these two scientists were actually working at Bell Labs, not on cosmology, on satellite phones, but they basically discovered what's called the cosmic microwave background. So basically they found that they had this persistent source of what they considered noise. And what this was is the radiation in the microwave that is the afterglow of the Big Bang. So basically, a long time ago in the history of the universe was opaque to light. And then as it expanded and cooled, sort of the plasma that was preventing light from freely streaming went away. So the electrons and protons recombined. And you had the first light that was able to freely stream throughout the universe. And this light is referred to as the cosmic microwave background. So cosmic because it's basically a map over the entire sky, microwave because it's in the microwave, and background because it's a very low intensity. And so from the discovery in the 60s, you have increasingly sophisticated attempts to map this out. So the Coma satellite in 1989 mapped out the anisotropies in the CMB, and then the resolution has improved over time. And so Planck is sort of the gold standard today. So here we can see just a full sky map of the CMB. And so what these little red and blue substructure is, that comes from actually fluctuations in the matter density field at early times.
That's Argos, right?
This is everything. This is the entire sky. Yeah, so
Can you apply cognition from dark matter for that?
that's a great question. Yes. So in fact, this map requires dark matter, but that's, so I'll explain it. So basically here you're seeing something that has some relationship to the matter density field at early times, right? So there are fluctuations in this map. Visually, they've been enhanced, but there are very small fluctuations in this map that correspond to fluctuations in the matter density at the time of the CMB. And so when people discovered the CMB, they found that these fluctuations were not big enough to account for the matter, the sort of the structure that we observe today, right? So these fluctuations come from the baryonic matter, right? Because they basically what has happened is baryonic matter at the time of the CMB has emitted light to us. And so what was required then is a second type of matter called dark matter, right? That doesn't interact with light and therefore can start forming structures earlier. And then when the universe becomes transparent to light again, the baryons can catch up by falling into the potentials that are there made by the dark matter. So the reason that I sort of took this digression about the CMB is that we actually identify clusters with the CMB. So there's sort of an effect called the Sunyaev-Zeldovich effect. So it was first written about by Soviet physicists in 1970. And basically what they showed is that if you have CMB photons coming in the foreground, when they go past through a cluster, right, the hot gas within the cluster will upscatter the energy of the photons. And so when you actually look in the CMB maps, you can find clusters. So here is our friend, the Coma cluster, in fact, in the CMB. So you can see that there's an obvious peak here. And then the next fact that I want to explain before talking about clusters in more detail is that clusters also shine in the X-ray. So this was discovered in the 70s when people finally put up telescopes into space to observe in the X-ray. And here you can see the Coma cluster again is very bright in the X-ray, right? So there's tons of hot gas in the X-ray that is in clusters that will put out X-rays that we can observe. So here, for instance, is an example cluster observed in three parts of the electromagnetic spectrum. So the X-ray, the optical, which is just us seeing tons of galaxies all in the same place, and the microwave. So cluster cosmology, basically the part of the problem, right, is identifying the clusters in whichever wavelength band you're using, and then studying their properties and their distribution. So here I'm just showing plots that kind of illustrate the pros and cons of these three methods. So I'll just say it in words, in simple terms. X-ray and SZ produce very nice data, but they can only find so many clusters. So they can only go so far down in cluster mass. So they produce excellent samples, but they're relatively small. Optical, which is basically looking for tons of galaxies, produces huge samples, but those clusters suffer from tons of selection effects that make it difficult to interpret them. So here, what these plots are just showing is sort of the number of clusters that you can get per distance away from us for different surveys. So LSST and DES are optical surveys. eROSITA is a X-ray survey, and then these two down here are SZ surveys. And you can see that the SZ surveys don't produce huge samples of clusters, but they have very excellent quality. And the same can be said with eROSITA, which is X-ray. So at low redshift, it produces competitive amounts of clusters. But then as you go further out, it drops below the two optical curves. So sort of the standard way that clusters are used is once you've identified them and defined your sample, you use the amount of clusters per mass to tell you something about cosmology. So here I've just made a plot that kind of schematically explains this. So on the left-hand side, in each plot, we have sort of a reference number of clusters per cluster mass, right? So objects form hierarchically. So you have lots of objects at low masses, and then they merge to produce bigger objects, right? And so the black line is sort of showing a reference, and then each one of these panels shows what happens if we change some property of the universe. So if we add more matter, the whole curve goes up, right? This is increasing the matter density. If the universe has more structure in it, then this enhances the number of clusters, and particularly at the high mass end. And if we have more dark energy, the expansion of the universe sort of slows down the formation of clusters. So you've depressed the curve everywhere. And here I'll just show an example in actual data. So here are a plot on the left-hand side. This is for a cosmology that we sort of believe is consistent with the true universe's cosmology. So these numbers are just telling you how much matter and dark energy there are. So this number is 0.25. That's saying there's 25% of the matter energy budget is in matter. And this number is 0.75. So that's saying 0.75 is in the form of dark energy, right? And so here, this model of cosmology fairly well fits the data, right? Which is the number of clusters as a function of mass for two different redshifts. So this is clusters at a certain distance from us. And if you can see that if we take a model where there's no dark energy at all, the model completely fails to predict the data, right? So particularly this blue line is completely offset from the points. So this is just an example of how these cluster abundances are used to constrain cosmology. So now I'll just show a couple other ways that clusters can inform us about cosmology. So one is that they can constrain our theories of gravity. So at the beginning of the talk, I told you that we believe that the universe is governed by a theory of gravity called general relativity, but people can come up with different theories, right? And so one requirement of these theories is that they all have to sort of reduce the general relativity in the solar system. So they have a mechanism that's called a screening mechanism, where they are the same in high density regions such as our solar system, but can differ from general relativity in lower density regions. And clusters are a perfect sort of laboratory for distinguishing between these two different theories, because when things move into a cluster, they're going from an unscreened region into a screened region. And so here we have a simulation, and at the center of it is a massive cluster. And each one of these little arrows shows the position of a halo, sort of a discretized structure of dark matter. And the direction and length of the arrow shows its velocity. And so you can see that there's two colors of arrows. The gray is what you get in general relativity, and the red is what you get in a different model of gravity. So in this case, it's a F of R model. But in any case, it's a model of gravity where you enhance gravity in low density regions. And so you can see that the velocities are completely different, right? So in general, the red arrows are longer, and they also have different directions. And so this you can see in a plot on the right. So this is showing just the difference in velocity with respect to general relativity as a function of distance from the cluster. And you can see that there's a huge difference as you get in towards the cluster. So the galaxies or particles are falling in towards the cluster. And in the model where gravity is stronger in the unscreened regions, you're sort of adding up this enhancement over time. And when you get toward the center of the cluster, your object is moving a lot faster. And the final method of cluster cosmology that I think is interesting is that clusters can maybe add a new rung to this distance ladder. So the way this is done is that if you look at the velocities of galaxies around clusters, and you look at this as a function of distance from the cluster, which is being shown here, you eventually reach a point where they flatten out, right? And so this edge is telling you something about the velocity structure of the clusters. And as I've shown, right, the velocities of galaxies in a cluster are related to the cluster mass, and therefore its size. So the idea here is that if you can observe this edge, which is also seen in the data on the right, then you can get a standard ruler that you can use to measure distances and therefore measure the expansion of the universe. So this is actually, to me, is very exciting. This is like very new work from some of my collaborators. So I will just end by telling you about some of the questions that remain today. So sort of the great debates of the present day. So here we just have two plots, and they're very similar, in fact. So the issue in both plots is that the cosmology that you constrain from the CMB is different than what you constrained from today. So on the left-hand side, this is showing the amount of structure for a bunch of experiments. The black line here is from the CMB, from this Planck satellite. And you can see that it basically disagrees with all of the values that people constrain from other experiments that use physics from late times. And this is basically seen analogously in terms of the expansion. So here, this is the Hubble constant, basically measuring the expansion rate. And if you look at the measurements from the CMB up top, they all disagree with how we measure these things at the early times. So these are sort of two tensions, as they're called in cosmology today, that need to be resolved. And that resolution could be that there are sort of systematics that are biasing the measurements, or it could be that there's new physics that's necessary to reconcile these two plots. So with that, I'll end and take questions. Oh, yes. So the question was, do black holes play a role in dark matter? So I think that by now, I think the answer is no, but there was a possibility at earlier times. And I think that, were you going to say something?
there's still this possibility of primordial black holes, right? That haven't been really ruled out.
Yeah, but I think the
Black
issue.
hole in really, really early universe hasn't been ruled out yet.
I think the issue is that they have to figure out how to form. So they have to figure out how to form them, right? Basically, it's getting squeezed on from many directions, right? So first they have to form, right? Second is that if they do form, they can't basically radiate themselves away. So in black holes, a smaller black hole basically radiates more energy and will dissipate essentially. And then on the other end, they can't be too big, because if they were very big, then you would expect to see lensing events from these dark matter black holes. So I think, yes, it's right that it's still on the table, but I think it's sort of the window of possibility is closing very fast. Yeah.
So Andres, in your last slide, you were showing what is now the great debate in modern cosmology, basically.
Right.
Between, and notice the numbers for H naught there are like high 60s in the early universe and low 70s in the late universe. So there's not a really large gap there.
Right.
But the assumption there is that the Hubble constant is a constant, and it's not a Hubble parameter that is dynamic, that could change over time. So my question is, are there researchers trying to model the universe with a variable Hubble constant or Hubble parameter?
Yes, I think those models are solutions to this tension, but I don't think any of them work yet to resolve it, basically. Yeah, but that could be a resolution to this. Yeah, so the CDM. So I think if you relax that, then you can potentially force these to be consistent with each other. Yeah, and the same applies to the left-hand plot, which is a discrepancy in the amount of structure that we observe.
One of your at the beginning of your talk, you had a slide showing the two pie charts.
Right.
Yes. I believe the bottom pie chart was sort of what percentages of what the universe was consisted of in the early days and then what it is now. So why has it changed?
Repeat the question. Sorry, I should have done.
Oh, I'm sorry. Okay, so this question is why do these pie charts that are shown on the right-hand side, why do they develop over time? So part of it is expansion. So dark matter and atoms are not created. Part of it is that less photons are created. And then the main issue is that expansion occurs, right? So the reason that dark energy is dominating now is because as the universe expands, the dark energy takes over more of the energy budget of the universe, and this essentially downgrades dark matter and atoms.
One of the slides show the correspondence between the relativity cluster and the light activities.
Oh, right, yeah.
So I want to know if those that correspond this model to study the population dynamics on Earth or the economic dynamics. Because from I can perceive this with the more brighter in the area, the more economic activity.
I mean, I would be fascinated to learn about it. For me, it's just an example. But yeah, I mean, I think definitely, the problem is that we've only had pictures of the Earth from space for, since the 20th century, right? But yeah, maybe it's possible. The economists have to get on that, I suppose. But the inspiration of this plot was that my advisor he collaborates with the artist, and they sort of make these light bulb sculptures that sort of represent clusters and galaxy distributions. So I realized that he is actually he's a very biased tracer of the people distribution, in that he has like hundreds of light bulbs associated with him, whereas most of us have maybe like, I don't know, 10. So yeah. But yeah, I would love to read about if someone did that. It would be fascinating, right?
You go back to the side of the bars and arms.
Oh, yes, the simulation, yes.
Yeah, that one right there. My thought was that galaxy evolution shows that some of this structure turned into beta elliptical galaxy from a state in a photograph from there to a big elliptical galaxy.
Right.
How say other photos of the Coma cluster, all those guys are all ellipticals.
That's right, yeah. So yeah, so that's a good question, yeah. So I've been inconsistent, but I will remember this time to repeat the question. So the question was, in the figure, basically, the galaxy has a spiral arm and a bar for a while, but eventually evolves into what sort of looks like an elliptical galaxy. And if you go back to, right, so the picture of the Coma cluster, you can see that a lot of the galaxies in the Coma cluster are indeed elliptical. So yeah, it's a good question. So, I mean, the answer is that we do see tons of galaxies with bars and arms. So it's sort of, there's a quantitative argument that you can make to say that, so these these t equals 0 through 10 are not in, years or units. But basically the argument would be that if these things dissipate on their own this quickly, you just wouldn't see that many of these, and you do see tons of them. And then to address the question about the ellipticals are also sort of evolving down the morphology relation of galaxies because of mergers as well. But it's a good question, yeah.
So I have two questions. It's the rotation curve where we compare that method is. So I'm just wondering what rotation curve we have the expected and then what is actually observed, and then we compare that method from this. But I'm just wondering what if we would have to redefine our understanding of gravity on cosmological.
Right. So there are, oh, yes. So the question is basically, could this be resolved with a different theory of gravity, right? Is that a fair restatement? So there were attempts to do this. So these were sort of called modified Newtonian dynamics theories, or MOND. And actually they do work very well to describe these rotation curves, but they don't work to explain the CMB or sort of the large scale structure of the universe. So it is possible, I suppose, that there could be a sort of modification to gravity that can simultaneously explain this and the large scale structure, but it doesn't exist yet. So I would say, I think that actually the CMB, which was this, the CMB sort of kind of really shifted the debate in favor of dark matter, because those theories, they work for galaxy rotation curves, but they cannot basically explain this phenomenology. And you said you had a second question, right?
Yes.
Yeah.
My second question is about the Hubble.
Right.
All the models we are using to estimate the Hubble that are lambda coded matter models. I don't know, don't we think that neglecting periodic effect in these models as little as they are in our universe maybe contribute to something?
Oh, so right. So the question was, in the Hubble tension plot, if sort of the baryons are playing an important role. So when I said that these assume lambda CDM, I mean, part of lambda CDM is the baryons, just they're 5% of the total sort of matter energy budget. So they're not included in the acronym. But I mean, so baryonic effects may be the resolution to this, because these here are basically relying on the distance ladder, which is calibrated by different classes of variable stars. And so if those are miscalibrated, then that could be the solution. And then on the top side, it could be that cosmology has to be updated. So in that sense, baryonic effects are in play. Yeah.
Questions. Does the universe follow in any way this spinning of our galaxies? Or is the universe rotating?
No.
It's just from the center.
Well, so let me restate the question, but the question was, is the universe rotating? And right, so it's expanding, but there's no sort of point that it's expanding from, right? In any point of the universe, you'll see this is called the cosmological constant, that the universe is on large enough scales, the universe is isotropic, meaning that it looks the same in whatever direction you look, in homogeneous. So it looks the same wherever you are in space. Yeah.
Question is, there's a correlation between the light observed and mass.
Right.
There's a given. Did that take into account the mass of the black holes at the center of the galaxies?
Right. So, okay, so the question was, so when this argument about the inferred mass from the light is made, does that take into account the black hole in the galaxy? So in Zwicky's time, I think it would have to be definitely not, because I don't think that they had sort of appreciated that black holes existed. But in any case, so this is related to the question about whether or not black holes could account for the dark matter. So basically, yeah, so black holes, I mean, the sort of the size of the black hole that could account for this has been basically the range of sizes that could possibly account for dark matter is being sort of squeezed out. But it's still a possibility, I suppose. But when Zwicky made the argument, certainly not. Yeah. And the mass to light ratios at that time were still, very uncertain as well. But the thing is that when his measurement called for just an unreasonably large mass to light ratio. So even given the uncertainty, it was still sort of a serious discrepancy. Yeah.
Do we have any idea of what dark matter and dark energy are? The total mystery still.
So people are trying to detect the dark matter. For me, I'm not so up to date on those kind of efforts. Actually, sorry, I keep on forgetting. But the question is, do we actually know anything about the particular nature of the dark energy and the dark matter? So in the case of dark matter, there are direct detection efforts. There's also sort of, I mean, you can sort of learn things about the properties of the dark matter from astrophysics as well. So whether or not it's self-interacting, that's something that people study. So if it is, then that may change the dynamics of a galaxy, for instance. So those efforts are ongoing, no direct detection as of yet, and no strong indication of self-interacting dark matter. For the dark energy, I think it's very uncertain. And part of the reason that people want to, oh, sorry, wrong direction. Right. So part of the reason that people want to update gravity is that so most of the models of gravity that people propose also can explain the accelerated expansion of the universe and sort of make this cosmological constant unnecessary. Whether or not that actually solves the problem, I mean, at least these models are called F of R, so they modify something called the action. So they can make that modification and sort of explain dark energy, but then you would be having another question, which is why is the action that way, right? So the dark energy question is like very open, definitely, yeah.
On matter, so, as a layman, I hear the word matter and I think of, something solid. Plastic bottle. Should I not think of it that way when I'm thinking in terms of dark matter?
I think so, because dark matter doesn't interact with charge. So, I mean, this plastic bottle the atoms are sort of kept together through electromagnetism. So in the case of dark matter, that can't be if that were the case, then we would have sort of observed it already.
Right.
Yeah. So, and I mean, if it's black holes, then I don't know if a black hole is solid or, yeah. Or, so, right. So someone said, or neutrinos. So neutrinos were a possible solution, but I think, what'd you say?
They're too hot.
Right, exactly. They're too hot, right? So what does that mean? So I don't know, I have to come up with a good analogy for this, but I mean, basically, if neutrinos were the dark matter, then they would wash out the structure that you see. So they're so-called too hot. So I told you at the very beginning, right, that the model is called lambda CDM. So the C here stands for cold. So yeah, so neutrinos were, I think people really neutrinos were an attractive possibility early on, but people realized that, yes, they're too hot. So the structure you see can't have been formed by neutrinos because they'll just dissipate basically. Yeah. But I should say that neutrinos have an effect on the matter distribution. That is something people study.
If there's no more question, that's like Andres again. For coming, I'll see you next month.